This is lesson 5.4 in geometry. We're going to be talking about medians and altitudes today. So first of all, I just wanted to do a quick review of what are the different segments that we've talked about that are special in triangles. So first of all, a perpendicular bisector, it tells you what it is, right? The two things it does, it's perpendicular to a side of the triangle and it hits a midpoint, so it bisects the side. Okay, an angle bisector has to go through a vertex and bisects the angle, so it creates two congruent angles. A median, which is one of the things we're going to focus on today, goes between a vertex and a midpoint. That means you have to see those two segments marked. And then an altitude goes from a vertex and makes a right angle with the opposite side, or the extension of the opposite side if it happens to be an obtuse triangle. Now, we also talked about mid-segments. They were kind of their own lesson, but remember, a mid-segment will join a midpoint of a side to a midpoint of another side of the triangle. Okay, that's a mid-segment. And the mid-segment theorem said that a mid-segment is parallel to the side of the triangle that it does not intersect, and it is also half the length. So whatever this is, that length is double. All right, so jumping into lesson 5.4. So reviewing the definition here, a median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. Okay, they are a vertex of the triangle and the midpoint of the opposite side. Okay, it happens that the medians are all concurrent. Now that word means that there are three or more lines that all intersect in a single point. Okay, the term concurrent refers to three or more. Because if two lines intersect, you just say they intersect. Okay, but concurrent means three or more lines that intersect in a single point. So again, two lines intersecting, we just call them intersecting. Three lines don't have to be concurrent because if you look at that picture, for example, they can form a triangle. Or same thing with four lines, they don't have to be concurrent either. So concurrent looks like if you have lines that are intersecting and they all come together in a single point, that means concurrent. Of course, those could be segments, rays, whatever, but generally talk about lines. Okay, so medians are concurrent. So the medians of a triangle are concurrent at a point, and that point is called the centroid. Okay, the centroid is the point of concurrency for the medians. So special word for medians is centroid. So when you look at a triangle that has all of its medians drawn, you're going to see, and again on this picture, F to H, that's the midpoint of the opposite side, so that means that's a median. And then from vertex to opposite midpoint here, that's a median. And then from vertex to opposite point here, that's a median. So when you draw in those three medians, they are concurrent at a point in the triangle. And that will always happen. Okay, every time you draw the three medians of a triangle, they'll always be concurrent. Now, the fact about the centroid is that its distance is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so another way of saying that is if you were to walk from a vertex and walk along the median to the opposite midpoint, when you reach that that centroid, you will have walked 2/3 of the distance. So in that median, this is a 2/3 of the whole thing. This is 1/3 of the whole thing. At every vertex, if you walk along the median at the 2/3 distance, you'll hit the centroid, and then the rest of it's 1/3. Okay, so when I said it's closer to the side of the triangle than it is to the vertex, that means you're starting at the vertex and walking toward that opposite point. So another way of saying that is that if you compare the ratios, this will be a 2-to-1 ratio, right? This is 2/3 of the whole, and that's 1/3 of the whole. So that's a 2-to-1 ratio. So the centroid divides each median into a 2-to-1 ratio. Now, if you were to draw other segments like altitude or all of the perpendicular bisectors, they actually also will all be concurrent, but they won't give you the centroid. They'll give you something else, and it doesn't have this fact. This is special when you draw medians and you create the centroid where they are concurrent. Okay, so again, on each one of those medians, it's broken into a 2-to-1 ratio. Okay, so if you think about kind of breaking that up, this is 2 and that's 1. That means that this is 2/3 of the whole and this is 1/3 of the whole, because the whole thing would be 3. Okay, 2-to-1 ratio. So for example, DJ is 15. So that's from D to J. Okay, so the whole entire median is 15. So CJ is the short part of that. That's 1/3 of 15, so it'll be 5. And then the rest of it is 2/3 of 15, or the remainder of the 15 when you take away the 5. Okay, if HC is 7, so we're looking at HC here. If that's 7, then to find the other 2 lengths, you can either say 7 times 3 will give you the whole entire length. That's HF. Or you can say 7 doubled. There's 7. That means this is 14. And then 14 plus 7 will give you 21. Okay. If CE is 18. CE is 18. That's the longer of the 2 segments, because again, the centroid is closer to a side than it is to a vertex. So this is the 1/3. This is the 2/3 of the whole median. Okay. So if I give you the 2/3 length, the way I think is easiest to think about it is just divide that by 2, right? So if CE is 18, that's going to mean that the shorter segment is half of that, it's 9. And then you can either do 9 times 3 is 27, or you can do 18 plus 9 is 27. Okay, the centroid has some properties that are helpful to know. So as we talked about a minute ago, the centroid divides each median into a 2-to-1 ratio. Okay, so that means again, the distance from the vertex to the centroid is twice the length from the centroid to the midpoint of the opposite side. The centroid is the balancing point of the triangle. Now what that means is if you have like a triangular mobile that you want to hang from the ceiling, like from a string or from a wire, you need to locate where the centroid is, because that means that the mobile will hang horizontally and it won't be tilting. Okay, same thing if you want to suspend it from like a post. If you have a triangle, like a plate or something, you know, sculpture that you want to put on a post, you need to find the centroid. And because it's the balancing point, it always lies inside the triangle because, first of all, it's the balancing point. You can't balance a triangle on a vertex or on a point that's on the side of the triangle, certainly not on a point that's outside the triangle. But then also, because all the medians are going kind of inside the triangle because they're going from a vertex to the opposite midpoint. So of course, the point where they meet is going to be inside. And then lastly, the formula to calculate the centroid. This is nice because we have a little calculation that we can do here. Try it again. We have a little calculation that we can do here. And this says it's kind of like the average, right? We're just averaging the X and Y of the vertices. And you'll see that down below. Okay, you're kind of finding like an average of the vertices to find that point. Okay, so this says find the coordinates of the centroid for the triangle shown below. So I'm going to start by using the formula and looking at these ordered pairs here for my vertices. So the formula that we just talked about is add the x's and divide by 3, add the y's and divide by 3. Okay, so 1 plus 5 plus 9 over 3. And then the y's are 1, 7, and 1 divided by 3. Okay, that's 15 over 3, which is 5. And then 9 over 3, which is 3. Okay, so 5, 3 is our centroid. Now, the other thing we can do is verify that using the definition. So I'm going to actually draw the medians now. So from a vertex to the opposite midpoint, you can tell that that point right there is the midpoint. You could also calculate it by doing the midpoint formula, 1 plus 9 over 2 and 1 plus 1 over 2. Okay, would be 5, 1, which is what that point is. 5, 1. So this one's kind of easy to eyeball where the opposite midpoint is, but if it wasn't, you could calculate it as well. Okay, H, they've actually labeled there for you, that's the opposite midpoint, and then G, that's the opposite midpoint. Now remember that those are all medians, and the point of concurrency of the medians is the centroid. So that means that the point that we just located, I kind of missed my median here a little bit. The point that we just calculated is the centroid, and that is the point right there. Okay, now it's not a coincidence that that point is 5, 3. So 2 ways to find the centroid. Use the formula or draw it on the picture and figure it out. Sometimes the centroid won't be a nice value. So because you're dividing by 3, you can end up with like a 1/3 or something. So that means that in that problem, you would need to use the formula and not the drawing. But a lot of times you can see it when it's on a coordinate plane, you can see where the centroid is. Okay, which segment is a median? Remember that a median has to go from a vertex to a midpoint. So I see a midpoint here, but that segment is not a median. It's not going to the opposite vertex. So don't know what that is. Okay, I see a midpoint here, and that one is going to an opposite vertex. Okay, so from vertex to opposite midpoint, segment AD is a median. Now, if I had known that these segments were congruent, and I joined from E to G, that would be a mid-segment. Remember, a mid-segment goes from vertex to, from midpoint to midpoint. Okay, so difference between a midpoint, a mid-segment, and a median. All right, second idea. So we talked about medians and centroids. Now we're going to focus on altitudes and their point of concurrency. An altitude of a triangle, this is the definition, is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. Now, the reason I'm saying it that way is because with an obtuse triangle, and I drew this for you before, but in an obtuse triangle, two of the altitudes actually lie outside of the triangle. Okay, so here's definition for altitude. And again, on the picture here, an altitude goes from a vertex and it makes a right angle with the opposite side. It has to do two things: vertex, right angle. If it happens to be an obtuse triangle, an altitude can be outside of the triangle. And if it's a right triangle, it can be a side of the triangle. And we've talked about that as well. Okay, we'll look at the pictures down there below in a second. And then again, remember, an altitude of a triangle is the same as the triangle's height. So this is an obtuse triangle, it appears. So if I wanted to draw the altitude from vertex C, it would need to be perpendicular to the opposite side, which is AB. And for it to be perpendicular, I would need to extend that side out. I'm just kind of eyeballing this to make it look like it's perpendicular. That looks pretty good. Okay, and see how the altitude is outside of the triangle. And again, that's happening because that's an obtuse triangle. Okay, theorem, concurrency of the altitudes. Now, it also happens that the altitudes of a triangle are concurrent. Okay, the point of concurrency of the altitudes is called the orthocenter. The orthocenter. So just like the altitudes can lie inside, outside, or on the triangle, the orthocenter can also be inside, on, or outside the triangle. So here are three different kinds of triangles. So here's an acute triangle. Now again, we're talking about altitudes. So the altitudes go from a vertex perpendicular to the opposite side. From a vertex perpendicular to the opposite side. From a vertex perpendicular to an opposite side. Okay, so those are three altitudes. You can see on the picture that that's the point of concurrency. That's where they all meet. Okay, where is the orthocenter? Well, it's inside the triangle. Okay, here's a right triangle. And we discussed this before as well. So when you draw an altitude from the vertex to the hypotenuse, and then from a vertex to the opposite side here, ends up being a leg of the right triangle. Okay, and then the altitude from this vertex perpendicular to the opposite side also ends up being a leg. So two in a right triangle, two of the altitudes are actually legs of the right triangle. There's one altitude that lies inside, and it's the one that goes from the right angle to the hypotenuse. So in this picture, where is the orthocenter? Well, the orthocenter is where they all come together, and that's happening right there. Oops, sorry about that. That's happening at that point right there. So for a right triangle, the orthocenter is on the triangle. And where is it? Well, it's at the vertex of the right angle. Okay, so if it's an acute triangle that you're looking at, when you draw the three altitudes, the orthocenter, the point of concurrency for the altitudes is called the orthocenter. The orthocenter is inside the triangle. If it's a right triangle, the orthocenter ends up being on the triangle at the vertex of the right angle. And then for an obtuse triangle, I think it's helpful if we highlight, let me try that again, make that a little bit skinnier. I think it's helpful if we draw, highlight the triangle that we would have started with. Okay, that's our obtuse triangle that we're starting with. Now, the altitudes are from this vertex perpendicular to the opposite side. Means you would have to stretch out this side and then draw your perpendicular. Again, this is an obtuse triangle, so the altitude lies outside of the triangle. There's one altitude. And then from this vertex, the opposite side is here. This is the opposite side. So we're going to stretch that out and draw the perpendicular like this. Again, that's supposed to be perpendicular to the line containing the opposite side. And then our last altitude needs to go from a vertex perpendicular to the opposite side, which means it lies inside. However, if I want to find the point of concurrency, I'm going to stretch this out until I see where it crosses the other two altitudes. Okay, here's the point of concurrency for the three altitudes. This is an obtuse triangle. The orthocenter will be outside, just like two of the altitudes are outside. The orthocenter is outside the triangle. And its location is going to be kind of like behind the obtuse angle. That always happens with an obtuse triangle. So again, I want to emphasize that altitude is the segment. Orthocenter is the point where all the altitudes come together, okay? For medians, that point's called the centroid. For altitudes, it's called the orthocenter. The generic name is point of concurrency. When three or more lines intersect, you get what's called a point of concurrency. Okay, so for orthocenter, let's do a little highlighting here just to recap that. The orthocenter for an acute triangle is inside. Okay, for a right triangle, the orthocenter is on the triangle. And then in an obtuse triangle, the orthocenter is outside the triangle. Okay. Centroids are easier because centroids is always inside, but orthocenter, it looks a little different. The other thing though is that orthocenter doesn't really have a lot of interesting properties. Okay, just a couple quick examples here. So it says identify a median. Remember that a median goes from a vertex to the opposite midpoint. So where would there be a median? A to D. Segment AD is a median because it goes from a vertex to the opposite midpoint. Again, that's not a centroid, that's a median, it's this segment. Identify an altitude. So an altitude needs to go from a vertex perpendicular to the opposite side or the line containing the opposite side. So the only place there's a right angle there is segment CF. Okay, so if we look at these different segments here, the picture is showing you some different terms. We have talked about centroid, and again, that's from a vertex to the opposite midpoint. Vertex to opposite midpoint, vertex to opposite midpoint. Okay, the centroid goes along with the medians. Okay, then we talked about the altitudes, and that was orthocenter. Orthocenter goes from a vertex perpendicular to the opposite side or the line containing the opposite side. So these are all altitudes. And the point of concurrency of the altitudes is the orthocenter. Okay, and then there's two other points of concurrency we haven't discussed yet, but you can tell from the picture what the incenter is the point of concurrency for. So if you look at what the drawing shows you, that point right there is the point of concurrency of three segments. Well, rays, lines, whatever. Okay, and you can see on the picture that we're going from a vertex and we're cutting the angle into two congruent angles. Okay, we're going from a vertex, cutting this angle into two congruent angles. We're going from a vertex, cutting this angle into two congruent angles. So that means those are angle bisectors. And so that's a term we haven't discussed yet, but certainly something that is true. The angle bisectors intersect or are concurrent at a point that's called the incenter. Right? And then over here, circumcenter. Well, what are the segments that are being drawn to create the circumcenter? You may not, I don't know, this may not be the greatest picture ever, but what this is supposed to be showing you is the perpendicular bisectors. You may notice that there's not quite the marks that you need there, so I'm going to go ahead and add those in. That should have been already drawn on the picture. Those have to be congruent, these have to be congruent, and these have to be congruent. So remember that a circumcenter, sorry, I don't mean that. Remember that perpendicular bisectors are segments that go perpendicular to a side of the triangle through its midpoint. Okay, perpendicular to a side of the triangle through its midpoint. And then perpendicular to a side of the triangle through its midpoint. So you have to have the right angle marks, and also it should have been marked as those were being midpoints. And so the circumcenter is that point of concurrency right there, and it comes from the perpendicular bisectors. Circumcenter is the special name for the perpendicular bisectors. Okay, so the four special segments that we're focusing on: altitudes, medians, we've already discussed in this lesson, orthocenter and centroid. And then in a different lesson, we would discuss incenter as angle bisectors and circumcenter is what you call the point of concurrency, the perpendicular bisectors.